Hi and welcome to Bro Abhiyantriks. In today's video, we are going to talk about strain energy in specific. Now, without any further ado, we'll start with the explanation of, first we'll deal with some theory concepts and we'll talk about some formulas and then we'll directly jump into the problems now. Okay, what exactly is strain energy? Strain energy is the total work done by the load. So as simple as that. So usually we'll go with the letter U to denote strain energy, and this is given by half into the load into the displacement, or the force into the displacement, so which is nothing but the work done. So now if I substitute the value for delta here, for a prismatic bar I'm going to have U is equal to P square L by 2AE. So this is going to be the formula that we are going to rigorously use while solving the problems on the strain energy, right? So what about the strain energy due to the self weight? So here U will be given by gamma square A into L cube divided by 6. Right, so here gamma is the unit weight, so here the W is given by gamma into A into the L, right? So and gamma is in the units kilogram, or let's say newton per millimeter cube or meter cube, right? So what about strain energy due to shear force? So because for shear force we are going to have we'll have to integrate in the surface, so we'll have shear force which is in the function of x square into dx divided by 2 into ax into the g, right? So here ar this is ar is the reduced area, right? So after the area has been loaded and unloaded, so we are going to have some reduction in the area, right? So we are talking about that. And the strain energy due to bending again is given by U is equal to integral mx square ds divided by 2 e into I. So I is the moment of inertia. And for the strain energy due to torque, so again we are going to have integral dx square into ds divided by 2 into g into ip. So ip is polar moment of inertia. Okay, so with these formulas, so let us try to solve some problems on strain energy. Some very basic problems. Find the strain energy stored in a prismatic bar as shown in the figure due to self weight. Also find the strain energy stored when an additional load P is applied at the free end. Okay, now the first case for this, that is the self weight. Now if we have a prismatic bar, I'm going to consider an element of length dx. Of length dx, which is x at a distance of x from the bottom of the bar. Now what will be the load on element? So which is nothing but px is given by gamma into a into dx, right? So now what would be the strain energy on this element? So the delta U is given by px square into dx divided by 2ax into e. Now if I substitute all the formulas in this, so I'm going to have gamma a into x whole square into dx divided by 2 into a into e. Now u is given by integral 0 to L gamma square into a divided by 2e into x square dx, so which is nothing but gamma square a into L cube divided by 2e into 3. So this is going to be the total strain energy on the load. Right, so the second part here is because of an additional weight as well. So I'll write a small diagram for this. So I'll have a prismatic bar and I'll consider an element of length dx from x from the bottom, and there is also an additional load acting. Right, so now for this, the load acting on the element px would be given by gamma into a into x plus p. Now the total strain energy of the element is gamma ax plus p the whole square into dx divided by 2 into a into e. Now this total strain energy is integral 0 to L, and if I expand this, I'm going to end up with gamma square a square x square plus p square plus 2 gamma ax p whole multiplied by dx, and in the denominator I have 2ae. Right, so if I simplify this, I'll have the strain energy will be given by gamma square a L cube divided by 6 plus p square L by 2ae plus gamma pl square divided by 2e. Right, so now moving on with the next question. The figure below shows three metal cubes A, B, C of side 100 mm in direct contact, resting on a rigid base and confined in x coordinate between the two rigid end plates. If upper face of the center cube is subjected to a uniform compressive stress of 0.5 kN per mm square, compute for cube B the following: the direct stress, the direct strains in the three coordinates, and also the volumetric strain. Right, so first of all, I'll try to solve the case 1, which is the direct stress. Right, so to find out the direct stress, I'll have to go with the compatibility equation. So first of all, I'll name the cubes. I'll name this as A, B, and C. So delta A plus, I'll only consider this in the x direction, delta XA plus delta XB plus delta XC totally is 0. Now I'll divide the entire equation by L, and delta by L is nothing but the strain. So that is nothing but strain in x direction for A, and strain in x direction for B, and strain in x direction for C block in total is going to be 0. Now I'll call this equation as number 1. Now to write other set of equation from equilibrium, I'll consider the free body diagrams. Let me just draw some schematics for this. Alright, so I'll consider body A, and the body A is going to be experiencing the compressive load. This is going to be sigma x. Right, so what about the strain equation for this? The strain equation for this is again nothing but minus sigma x divided by EA. Now for body B, again I will have compressive load for this, and also in the z direction I have the compressive load. So this is sigma z and this is sigma x. Sigma z is given by 0.5 kilonewton per mm square. Right, so now epsilon xb is given by minus sigma x by eb, and again plus nu into sigma z divided by eb. And now for body C, this is only going to experience compressive load sigma x. Now epsilon xc is given by minus sigma x divided by ec. Now if I substitute all of this in equation 1, I'm going to end up with sigma x into 2 by ea plus 1 by eb will be equal to 0. Right, not equal to 0, this will be equal to nu into sigma z divided by EB, right? So if I substitute all the values for this and if I simplify, I'm going to have sigma x as 0.041 kilonewton per mm square. This will be the total compressive load that will be acting on all the blocks. Now for the second point, the strain in all the directions for B. So here I am going to calculate sigma xb first of all, that is nothing but minus sigma x divided by EB plus nu into sigma z divided by EB. So which is nothing but, if I substitute here, this is minus 0.041 divided by EB plus 0.3 into 0.5 divided by EB. Now I know all of these values now, so this is going to give me 5.45 into 10 to the power of minus 4. Epsilon YB is again given by nu into sigma x divided by EB plus nu into sigma z divided by EB. Sigma z is compressive, so in the lateral direction, so I'm going to have the tensile force that is in y direction, right? So if I substitute all the values now, I'm going to have 8.11 into 10 to the power of minus 4. So I'm simply skipping all the substitutions here. Now epsilon zb is now given by minus sigma z, because this is compressive load, divided by EB plus nu into sigma x divided by EB, now which will give me the value of minus 2.44 into 10 to the power of minus 4. Now for the third one, the third question that I've asked, it is the volumetric strain. So volumetric strain is nothing but the summation of all the strains in all the three directions, that is sigma x plus epsilon x plus epsilon y plus epsilon z. And again, if I add this all of this up, I'm going to have minus 1.084 into 10 to the power of minus 3. This is going to be the total strain, the total volumetric strain of the body. Now going with the last problem of this video, again I have a composite bar as shown in figure. Determine the reactions at the two support and take E as 2 into 10 to the power of 5 Newton per mm square, right? So now for this, first of all, let me write the static equation. The static equation will be, now we have a tensile load here, a compressive load here, the opposite to this direction. So meaning I'll have a load something like this. I'll call this as R1, and this is going to experience compressive load, so this is going to come here, so I'll call this as R2. Now for the static equation, I'll have R1 plus R2 is equal to 25 into 10 to the power of 3. I'll call this as equation number 1. Now for the compatibility equation, I have delta of I'll name this as A, I'll name this as B, I'll name this as C. Right, so delta AB plus delta BC will be equal to 1 mm. So because I have 1 mm of clearance here for the material to expand. Right, so now if I write the free body diagrams, I have for the body 1, I'll call this as 1 and I'll call this as 2. So for the body 1, I have something like this. So this is R1, right? So for body 2 again, I have the loads will be R1 minus 25. So 25,000. I'll also consider the kilonewton here, right? So R1 minus 25,000. So here, if I if I substitute the delta values, I'll have R1 into L1 divided by A1 into E plus R1 minus 25,000 into L2 divided by A2 into E2. Now this everything will be equal to 1 mm, and if I substitute the values here, R1 into the length of the first material is 1000 divided by the area is pi by 4 into the diameter given as 10 square into 2 into 10 to the power of 5 plus R1 minus 25,000 into the length 2, which is 1500, whole divided by the area 2, that is pi by 4 into 15 square into 2 into 10 to the power of 5 is equal to 1. Now if I simplify this, I'll end up with R1 as 19.43 kilonewton and R2 as 5.57 kilonewton. A fairly straightforward question, and hopefully you've learned something from this video. Thank you for watching and happy learning.